All right, let us look at some complications that we're going to have with electron configurations, some things that you just need to be aware of because you can bet I'm going to test you on them. All right, first thing, let's look at the electron configuration of chromium, and we're going to be using the noble gas core shortcut because that's nice, and we'll be using the periodic table because that's nice also. So let's look at, here's chromium right here on the periodic table. The previous noble gas is argon. So with chromium here, we've got argon core. And then we would say, okay, argon core. Then we've got 4s2, 3d, 1, 2, 3, 4. Okay, 4s, 2, 3d, 4. But then something is interesting here. If we have 4s2, 3d4, if we drew our boxes, note 4s2, I like to put my electrons in red, one up and one down. 3d4, note how many boxes do I need to draw if I'm in the d orbitals? That's right, I need 5 boxes because there's 5 d orbitals. 1, 2, 3, 4, 5. Okay. Now, 4s2, 3d4, I need to put in my 4 electrons. How will I put in my 4 electrons? Good old Hund's rule. 1, 2, 3, 4. And what we notice here is that we are awful darn close to having a half-filled shell, subshell here. And what have we found out? Well, yeah, that's right. We found out that half-filled subshells, they're stable. And so it turns out what chromium is going to do is it's not going to have this electron configuration. It's decided that it's more stable, it's actually lower in energy to take this down electron and make it an up electron here. It is more stable for chromium to be 4s1, 3d5. Because 3d5 gives us 5 electrons that have the same spin and half fill that shell. All right, so what do you think is going to happen with copper? Well, let's take a look. Normally copper, well, where are we at here? Okay, here's copper, argon core. Normally it would be 1, 2, 4s2, 3d, let's count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9, oh, what do we see here, 3d9. What would happen if we took one of these 4s electrons and moved it up to this 3d shell? That would be 3d10. We have 10 electrons in the Ds, a full shell, very stable. So that's what copper is going to do. Copper is actually argon core, 4s1, 3d10. Okay. How are you going to remember this? I don't know, but you need to. The way I usually remember it is I just do it out instead of just memorizing what the exceptions are, although after you've been doing it for a while you get to know them. It's just like, I'm just going to figure it out. I will always draw the electron configuration how it should be, and then I look, oh wait, if I could move up 1 electron from an s orbital into the d orbitals, will that give me a half-filled or a filled shell? If yes, I know that's what the atom's going to do, and that will be the electron configuration. So, let's look at molybdenum, Mo, down here. Hint, it's right below chromium. Well, if I were wanting to figure out the electron configuration for molybdenum, I would have worked it this way. I would say, okay, it's krypton core, then 5s2, 4d, 1, 2, 3, 4. 4d4, and then I'm like, uh-oh, 4d4, one more electron in the 4ds, and it would be a half-filled shell. So I'm going to realize this will be krypton core 5s1 4d5. Should make sense to you that molybdenum does what chromium does. It's right under there. So the next one is silver. Guess what silver is going to do? Well, silver is right below copper. That's right. Silver is going to be krypton core 4s1. Whoops. Krypton core 5s1 4d10. Yep. Any guesses as to what gold is going to do? It's right below silver. Yeah, that is correct. Xenon core. And, ooh, gold's going to be interesting because we've got these F electrons to deal with. So let's deal with it. We're right here. Let's do it. Gold. What do we have here? Okay, gold is right here. Xenon is the next noble gas. Xenon core. But now let's look what we have here. Xenon core 54. 55, 56, 57, 58, 50, what? 55, 56, 57, 72. Can't do that. 55, 56, 57, 58, 50. Okay. Periodic table is telling me xenon core 6s2. Okay, so far so good. 6s2. This is 5Ds, but there's only one of them. 5D1. Then we're down to the 4Fs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, I knew that. 4F14. Then we're back up. Okay, here's 71. 72, 73, 74, 75. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 5D8. That's what the periodic table is telling me. Xenon core, 6s2, this one 5D, this 5D1, then 4f14, and then the rest of these Ds up to 8 more of them. And yeah, and you'll see some books that have it this way, but most of us say, hey, I've got my 5D1 here, I've got my 5D8 right here. Let's combine them, shall we? So that would be xenon core 6s2 4f14 5d9. And then your brain should say, wait a minute, the whole reason we looked at gold is because it was right under silver. We have 5d9 here. One more electron and we can fill up the D shell. Question though, if we did that, where could we get that electron from? Well, it could come from the 4f14, take one of these away, or it can come from the 6s2. What is going to be the easier thing to do? Which way is this going to work? The answer is it takes it from the 6s2. So the real answer for gold is xenon core 6s1 4f14 14, 5, D, 10. Whew. Told you this was getting complicated. Okay, question. Why did the goal decide, or when the electrons are in here, why did we promote electron from the s orbital to the d's instead of taking an f electron? The answer is because turns out this 6s orbital is higher in energy than the 4f orbitals, because note, this is quantum shell 4. If we've got all 14 electrons in here, in this quantum shell, then the n equals 4 shell is completely filled. A completely filled principal quantum shell is going to be much more stable. So this is our valence shell, n equals 6, even though we've got n equals 5 isn't filled already, but oh, check that out. This fills the n equals 4 shell. It also fills the n equals 5 shell also. So our only electrons are in our n equals 6 principal quantum shell, which is the highest energy shell. So yeah, promoting an electron from our highest energy shell down to fill the D shell and the F shell is just going to be a much more stable thing than having this, promoting this electron up and having a n equals 4 shell not filled. So that's why it's going to do that. Whew. All right, let's look at some more stuff here. Well, let's just go crazy, shall we? What's the electron configuration for uranium? Yeah, let's use the noble gas core shortcut. Ooh, uranium. Where's uranium? It's way down here. Uranium's right there. Okay. Well, what's the next previous noble gas? Well, 92, 91, 90, 89, 88, 87, 86. So this is going to be radon core for uranium. We're going to have the radon core. All right, I'm going to write that down up here. Radon core. All right, what's next? Radon core 7s2. Okay, radon core 7s2. Let's follow the numbers. What comes after our 7s2? 6, because of 3, 4, 5, 6 D. Whoop. 87, 88, 89, 104. 89 is in here. 6D1. And after 6D1 is 5F123. 5F3. All right, so we have radon core 7s2, 6D1, 5F3. Note, we did not go into the 6Ds anymore, so this is it. That's the electron configuration for uranium. Cool. What about europium? Well, here's europium right down here. So what's the previous noble gas? 63, 62, 61, 60, 59, 58, 57, 56, 55, 54 xenon. So I know my europium is going to be xenon core. All right, xenon core. Gotta go down to here. 6s2. 55, 56, 57, 58, 6s2, 5d1, s2, 5d1. 1, 2, 3, 4, 5, 6, 4f6. All right. Looks good, eh? Problem. How many orbitals in the F shell? Okay, quantum mechanics. If it's an F shell, that means L equals 3. If L equals 3, that means 1, 2, 3, 4, or L equals 3, that means -3, -2, -1, 0, 1, 2, 3. I just counted on my fingers 7. There's 7 orbitals. Oh, but I've got 6 electrons in there. Can we see? That with 6 electrons in 7 orbitals, 1, 2, 3, 4, 5, 6. We've got one more electron. If we had one more electron to put in there, this would be a half-filled subshell, which would be nice. So what electron's going to go in there? What's your bet? I'm betting it's at 5d1. So this is not correct. This is xenon core 6s2 4f7 to get that half-filled shell. All right. Now, these last couple minutes we spent a lot of time looking at really complicated ones. Good news. Most of the ones that we deal with on a daily basis, beryllium, oxygen, sulfur, chlorine, bromine, iodine, iron, and all these guys, they're normal. They aren't nasty. They don't have super complications. We just get some just nasty complications when we're way down here with our F block elements. And just something to remember about your chromium, molybdenum, and copper, silver, and gold. All right.